In this next series of videos, I'm going to talk about various regression pitfalls. So things that can go wrong with a multiple linear regression analysis that we need to watch out for. In particular, I'm going to cover non-constant variance. So this is where the constant variance assumption that underlies the multiple linear regression model is violated. Next, we'll talk about autocorrelation or serial correlation. So this is where we fail to take account of time trends in the model, and this can lead to violation of the independence assumption. Next, I'll look at multicollinearity, which is where highly correlated predictors can cause unstable model results. Next, I'll look at what happens if we exclude important predictor variables from our model, and this can lead to possibly making incorrect conclusions. Next, I'll cover overfitting the sample data, which is where we appear to have a really good model that fits the sample data, but when we try and generalize that to predicting out of sample, so to the population, we get poor results and poor generalizability. Next, I'll talk about extrapolation. So this is where we're trying to use the model results inappropriately, and we're trying to make predictions outside of the sample data range. Then I'll cover missing data. So missing data is when we have sample data and there are some missing values in some of the variables, and so we have decisions to make about which variables to include, not only based on how useful they are in the model, but how much data do we have for those variables. And if we have a lot of missing data for some variables, it might actually be better to exclude those so that we can increase our usable sample size. And then finally, I'll briefly talk about power and sample size. So this is something we need to think about when designing studies, because we know that in general larger samples give us more information and tend to give us better models. And so thinking about sample size and then also thinking about power, so the capability of the model to actually produce usable results. So if we're trying to detect certain effects in the model, certain relationships, we need a sufficiently large sample size to be able to detect those effects. So I'll start in this video by talking about non-constant variance, and then in the next set of videos I'll cover the other regression pitfalls. So for this example, I think I'll jump straight into the data. So I've got some data here which covers different countries. It's quite a large data set. And then I've got a measure of fertility rates and incomes and education levels. And I'm trying to build a model to predict fertility rates from income and education. So if we're analyzing this data, we might want to look at it first. So here's a scatter plot matrix of everything that's going on, and you can see right away that there's a bit of an issue here. For example, in this scatter plot with fertility and income, it looks like we've got very skewed distributions because most of the data is down at small values of each of those variables, and there's very little data for higher values. So in particular, it makes sense to take the logarithm, the natural logarithm of income, And that's usually the case with an income variable. We often have lots of low values and a few very high values, so we have a skewed distribution. And as we mentioned in an earlier video, it often makes sense to take the natural logarithm of such a variable. And so now if I look at a scatter plot matrix, things look a lot better. So there appears to be linear relationships in all those scatter plots. But we don't yet know whether a multiple linear regression model with these variables is going to be effective or not. So to do that, we actually need to fit the model. So here's a summary of the model, but what I'm going to do is I'm going to skip ahead and think about the residuals, doing a residual analysis to check the assumptions. So I'll calculate the studentized residuals, and then I'll draw a plot of the studentized residuals on the vertical axis and the fitted values on the horizontal axis. And let me just zoom into this so we can see it a little more clearly. So if I was wanting to check the constant variance assumption, the way that I do that is I think about moving across the plot from left to right, and as I do so, think about the variability of the residuals in the vertical direction. Okay, and you can see as I'm tracing across the plot, I'm tracing out wider and wider variability for the residuals. So the variance of the residuals, it's not staying constant as the fitted values change, it's increasing with the fitted values. And so this would be a clear indication that the constant variance assumption is violated for this model. So non-constant variance, if we have it as we do here, that can create technical difficulties with the model. For example, it can lead to inaccurate prediction intervals. I'm not going to cover this in this video, but we can do numerical tests as well to help diagnose non-constant variance. So Broich-Pagan and Cook-Weisberg both independently came up with a similar test for this, and there's details of this in the textbook. So if we find non-constant variance, such as in this example, what do we do about it? Well, there's a few things that we could try. One is to try transforming the response variable. Another possibility is to use something called weighted least squares or generalized least squares, or perhaps a generalized linear model. So I'm not going to talk about these last three. The book does go into a little more detail on these. But instead, I'm going to see if a simple response transformation might work. So if we do that, I might think about taking the natural logarithm of fertility. So I already took the natural logarithm of one of the predictors. Let's try taking the natural logarithm of the response variable too, and fit that model. So here's a summary of that model. But I'm just going to focus on checking that constant variance assumption. Let's see if this new model we get more reassurance that the constant variance assumption is okay. Zoom in again. Hello. Okay, is that the right plot? I guess it is. Yes, it is. So let's do the same thing as we did before. Let's move across the plot from left to right and think about the variability of the residuals as we do that. So right on the left of the plot, we've got 3 points, and the variance there isn't very big, but there's only 3 points. So there's not a lot of information here. So I'm not really going to get too excited until I get more points to work with, and I'm going to think about the variation, and it stays pretty constant all the way across the plot. Okay, it's certainly close enough to being constant variance all the way across, that I don't have any concerns about the constant variance assumption for this model and this data set. So just a reminder, this is what the residual plot looked like when we had y as a response variable. This is the one we just looked at when log y was used as the response variable, and the constant variance assumption looks a lot more reasonable in this plot. So that's an illustration of non-constant variance, which is one pitfall that we always need to look out for when we're fitting a multiple linear regression model. In the next video, I'll talk about autocorrelation, which is another pitfall to look out for.